And here we have Christian Jaimes, who is the most senior core developer we have in the building, actually.
Hello. Hello? OK, perfect. Welcome to the afternoon of day one of PyLondinium. Thanks all for attending, and thanks for actually paying your tickets, because you're going to pay actually the travel of the core developers. In September, we're doing a sprint here, a meeting with the core developers at Bloomberg, and you're funding us. Thank you. So, hi, I'm Christian. I'm from Hamburg, being Python for a lot. Oh, yeah. I usually use a widescreen because low contrast, but these displays are amazing. So, I'm a core developer, actually, OK, the date's wrong. Since 2007, actually, October, and maintaining mostly security stuff at Python. I'm also employed by Red Hat, working on a software stack called FreeIPA, which is identity management, a bit like Active Directory. And this talk is going to be about TLS SSL. And the agenda and takeaways for this talk is I want to give you like a high-level view what's going on if you do like HTTPS or open your browser, go to a website. Quick introduction to the SSL model, a bit like 3 minutes crypto 101, TLS Handshake, how certificates and public key infrastructure work, a peek preview at TLS 1.3, and finally some books and resources at the end. So this actually 3 hours of material condensed into a 45-minute talk and then shrink down to 20, hopefully 25 minutes. So I need to rush that a bit. Sorry for that. I will upload the slides after my talk at that address. So this talk is under CCD license. And I have some assumptions. So only assuming Python 3.6 or newer, and some things only work in 3.8. New version of SSL, new version of TLS, because the old versions are really bad, and also modern crypto. So don't get on the pitfalls of bad old crypto which you can use in old versions of SSL. At first, should you actually use TLS SSL? So the short answer is actually yes. The slightly longer answer is yes, really should. And there are a couple of reasons for that. And most people think, oh, it's very complicated, it's also slow, but there's actually only one performance issue. It's not yet widely used enough. And the rest can be optimized. And these days, in most cases, it's actually faster to use TLS SSL, which Troy Han showed with a nice animation. So that's loading a web page with lots of resources over HTTP. It takes like 8.5 seconds. No, almost 6 seconds. But if you go to HTTPS, you do like, bam. So it's much faster because that can use HTTP2 with some tricks and tunneling, which you can't do over plain HTTP. And that's usually much, much faster. And setting up TLS SSL these days is also easy because thanks to free search with Let's Encrypt. So there's actually no good excuses to do that. On the other hand, lots of benefits. So both privacy and security. So nobody can inject like malware if you're using like public Wi-Fi. It's faster. Google and other search machines bump sites with HTTPS higher. You get browser warnings these days if you use like password fields, and browsers are even considering to remove support for plain HTTP soonish, probably next year or the year after. So, but what is HTTPS or TLS SSL actually? So it's this green, small, funny. Wow, my laser doesn't work very well on display. So this green icon is what most people consider as secure connection. I'll have Wikipedia definitions because they're much better than me to condense something on in a short sentence. So transport layer security and SSL, the old name, are cryptographic protocols that provide communication security over a computer network. The TSL protocol aims primarily to provide privacy and data integrity between two communicating computer applications. So lots of things. Let's pull it apart. So TLS core features are encrypted transport, so nobody can read what you're doing if you do it right. You can run multiple applications over that, not only like HTTP, but also email, VPNs, and whatever. It has like integrity checks, so nobody can mess with your data. You can see if somebody messes with your data. Provides protection against replay attacks. So if you send money to your bank, do a transaction on your online banking applications, attacker can't replay that over and over again to get like all your money off your account. It also authenticates the server in a very strong way. If you know you're talking to the actual bank and not some man-in-the-middle attack. And it can also do what most we don't do that for browsers, authenticate the client with client certificates. And it's very extensible. So HTTP2 and HTTP3 build on several properties where you can extend the protocol. Protocol is actually not one. It's a whole suite of different things. Well, like IETF has some standard for that. There are a couple of numbers assigned, and the IANA, there's different standards. I only talk about actual TLS. There's also TLS over UDP, and there's something new coming up called QUIC, which is HTTP3. There's ASN1, that's the standard for like encoding data, like JSON 30 years ago. And there's this notorious public key infrastructure with X509 certificates, which is a bit complicated, but again. So the SSL model, that's the thing most people use if you use like pip, install your packages, is a very thin wrapper around OpenSSL, which shows through in multiple parts. The most important bits and pieces are this SSL context thing, which maps to SSL CTX pointer in OpenSSL, which is your configuration space, where you configure how you do the actual connections. Then you have the SSL socket, which looks like a normal socket wrapped in something that does all the encryption and protection for you. It also in other bit and pieces, you use async I/O. You don't use the socket directly. You use the memory I/O, bio, and SSL objects. And there's something you should never use anymore, the very, very old legacy APA SSL wraps socket. Oh, hope you can see that in the background. It's a bit low here. So if you do connection with the Python SSL model, it looks a bit like that. So you import socket and SSL. You create a context. Then you create a connection. And you wrap the connection in something that's actually the SSL socket. You need a host name and two places. I'll explain why a bit later. So this thing here under the hood does a bit more. If you pull that apart, then it creates a context. And since I'm ignoring the old versions, I also set the minimal version to at least TLS 1.2. And since I don't want to show in the first part of the talk what TLS 1.3 is doing, of the maximum version, we require certificate verification. We require hostname verification. And since we want to verify the certificates, we also need to load like the trust store, the root of the trust for all the certificates. And then we need to do a connection. So this socket create connection is just a wrapper that takes care of IPv4, IPv6, and just creates a socket connection with DNS lookups. And that's actually the endpoint then for communication. Then wrapped into a SSL socket. So that takes ownership of the socket and returns a instance of SSL socket. And yeah, now you can just do most of the things you can do for a socket over the SSL socket. And if you look what we're going to do next, so if you look what the socket can do, there's some properties, like you can get the ciphers, which is this mumbo-jumbo of letters and numbers that I will explain in a minute. The three different versions you can have. You have SSL version 1.2, or the last one is for 1.3. So crypto thingies, how does crypto work? So the very, very quick intro into crypto, very fast, what you need for SSL TLS. It's a bit like Lego blocks. You build stuff of smaller blocks and create a protocol of that. The first thing we need in a couple of places is we need to have like a fingerprint of data. So most operations can't be done on large amount of data, but you need to shrink the data down, make like a checksum. That's hash algorithms. You also need something to encrypt your data. It's called bulk encryption. A bulk means you can encrypt lots of data very, very efficiently, very, very fast, which are these days always symmetric key algorithms. So you have the same key for encrypting and decrypting. But you have to do it the right way. If you do it the wrong way, then you can actually see through what the encryption does. So that's an encrypted image of a logo you may recognize. So you need also a mode how you operate your encryption. And yeah, all modes are beautiful except ECB, not you. You're bad. That's the one where you can see the penguin or the logo. So there are different ways to chain them together. And also encryption does not secure your communication. So you can still modify the data. So you need something that's called authenticated encryption. And these days we use AAAD algorithm. They're called authenticated encryption with associated or additional data, where you do something like a checksum and the encrypted output. Or if you decrypt, you verify that the output is the correct output. We also need a couple of asymmetric crypto algorithms. It means you have like a public and a private key part, three major subparts of that are asymmetric encryption, signatures where you sign something, and something where you agree on a mutual secret. Asymmetric encryption we don't do anymore because it's bad. Signatures we do a lot. We need to sign data both for certificates and for the actual connection to verify that you talk to the right server. So the server has the private key, or the CA has the private key, and it signs something else. And with a public key, you can then verify that the peer, or the right peer, owns the private key. And key agreement protocols are, Wikipedia claims a bit color mixing. So you have private parts and public keys, and you send your public key to the other part, and magically through math and funny stuff, you both agree on the same result without actually exchanging the result. And an attacker can't do the same. So we have these building blocks. We have key agreement or key exchange. We have authentication. We have bulk encryption with the cipher modes, and we used a one-way hashing function, for some parts like max. And these build up this lovely acronym. So that's TLS with elliptic key Diffie-Hellman key exchange with RSA certs, AS228 for bulk encryption in Gauss counter mode with SHA-256 as MAC algorithm. Yeah, and the other one, that's a very old one we don't do anymore, like no encryption at all, and MD5 is also bad. But these don't look like the things I printed out like 5 minutes ago because, well, OpenSSL has a different naming standard. So the first one is the same as that one, and that also maps to that one, and this is a new one for TLS 1.3. So, oh, I'm in time, almost. Handshake. So, if you do a connection to a server, you have forced to shake hands and agree on multiple things. So if you do a connection like that, wrap the socket, and during that operation, you do a handshake. So you agree on multiple parameters. Parameters are, amongst others, which version you talk, which ciphers you can talk, and then a way to identify the server with a signature and certificates. And then after you have verified the server, you agree on a pre-master secret. That's the secret you can use to derive more secrets for bulk encryption verification. And finally, once you have done all the handshake, you need to verify that both sides have agreed on the same thing, and no attacker has like modified your ciphers to something badly. That's what you do in the handshake. And again, we don't do like the old RSA key handshake, the bad one. That's insecure. There are multiple blog posts why that's bad. We do the actual modern one using Diffie-Hellman. Looks like that. So the client says, hey, hello server, send me, okay, I can talk the ciphers. I support this version. Here's a random number you need later. And I want to talk actually to PyLondinium, server name indicator. The server replies to, sure, hello, I selected that cipher. I selected that TLS version to talk to you. Here's another random number. Here's a chain of certificates you have to verify. And here is a part of the secret. It's the Diffie-Hellman server parameters. And also, I used my private key to sign these parameters. The public key for that is in the chain. And please do something with that. The client says, OK, sure. I generate my own Diffie-Hellman parameters, verify that. And then I tell OK, I changed you my specs. And now that box here, the first part that's encrypted. The rest is all in public. And the client sent the information back. And now they have both agreed on the same Diffie-Hellman parameters, have a pre-master secret, encryption secret, verify the MAC, so the method authentication code of this whole handshake, and we're done. And now you have done the handshake, and the client can start to send actual parameters, like a HTTP request. We used Python 3.8. I added something for debugging, so it's actually a private method because we have no good IPA for that. You get the same information, so you see, OK, the client writes, client hello, server replies. So you can bit of debugging with that. So certificates, what we exchange, exchange here. So the server sends this 4.5 kilobyte block of certificates. So what's a certificate, and how do public key infrastructure actually work? So for that, I'm going to, again, do like verification. I verify the cert, I load some stuff, verify the host name. And the host name is needed in two parts. The first is you need to send it in the beginning so the server knows which virtual hosting you do, and also to verify the identity of the server. And a certificate is one certificate is a block of different informations. You have encoding, usually ASN1. The different ones, most people know this big block of base 64 with begin and certificates. That's this PEM. There's also P12, which is rather nasty. Or you can have just a binary format that's either called SIR or DIR. They come in pairs. So the server has a public and a private key. And the client only gets to see the public part and the signature made by the private one. And it contains in the payload the public key of the server, some metadata, some extensions, and the certs are always signed by somebody who issues the certificate. So you have like a notary chain. You have somebody you trust that signs something else, and again and again. There are lots of different fields. There's always a serial number. There's the subject. The subject of the cert, there's the issuer that issued the cert, there's how long the certificate valid, usually for, let's encrypt it 3 months. And subject public key information is the public key of the certificate, and a bunch of extensions, which can be constraints, key usage, subject alternative name, something with OCSP, and yeah, it's a lot. But the certificates also have different types depending on which parameters you set, like in the key usage and the extended key usage. We start always for trusting and verifying certs at the root CA, or the so-called trust anchor. And the root CA signs itself. So it trusts itself. And that one you have installed in your browser, your operating system, or if you use requests, ship with certify. And that one also signs intermediate certs, because the private key of the root CA is very, very sensitive, usually stored in a way that nobody can get to the private key anymore. And for data operations, you sign other certs. You sign an intermediate cert, usually or 2 of them in most cases. And they actually sign at the end your end entity or your server cert. So you have your end entity cert. That's mostly, for this case, for servers. You can also have certs for clients. You can have certs for email or to sign code. And special cases, it's this chain. So the root CA signs the first intermediate, the other one signs the second one, and then you have the server cert. And in this handshake, you send the whole chain except the root. And the client can then look up this chain, verify the chain, and verify the trust anchor of that. So trust anchors, where are they stored? So on Linux and BSD, it's usually in a PKI 11 model that is then dumped to a file. And so distributions and don't agree on the actual location. There's some of the locations where different distributions have them stored. On Windows and on macOS, it's a bit more complicated because you should not actually directly use the certificate itself, but you should just ask the operating system to verify something for you, which is something we can't use in Python yet. And how does the certificate look like? So I just dumped the one for PyLondinium.org 3 days ago. It's interesting because it's a certificate from a company called, where is it? So it's a domain, subject, issuer. So that's the issuer. So that's the issuer of the Great Manchester, Salesforce, some company. And it's SNI, Voltan, Cloudflare. Here we go. So it's from Cloudflare. That's the subject, and it had lots of subject alternative names. So we share for PyLondinium our certificates with some casino websites from, Club Vulcan Casino, Resident Slots, So Cloudflare hosts websites a lot, so they share the same IP address and the same server with a whole bunch of other ones. And remember, at the socket, I'll always supply the host name, because it's not only important to validate that the chain is correct, you also have to validate that the end certificate actually supplies to your host name. So if you don't verify the host name, then I can send you just any certificates, And yeah, you must make sure that it's also matches the host. And that's very complicated. In Python, we had like now 7 bugs. While updating the talk, we had a new bug coming in, which is not very critical, but still. So verifying that yourself is hard. And since 3.7, I switched to use OpenSSL. OpenSSL does this the right way. And if there's a bug, it's not my fault. So TLS 103, very, very quick. So TLS 103 is a new standard, came out last year. It killed lots of bad crypto. Horror story, this list is a whole list of horrible old crypto things. Use lots of shiny new crypto things. For example, it only uses the authenticated encryption algorithms anymore, only them. It improved the protocol in lots of different ways. They learned a lot from past mistakes and past attacks on TLS SSL. It's also much faster because what the client does, it does a one round-trip handshake. So the client makes an educated guess and says, well, you probably use that kind of Diffie-Hellman parameter, so it sends you a key share. The server says, yep, OK, I like that key share. And we're done. It's a whole handshake. And important to know is the certificates you get from the server are encrypted. The certificate chain here is already encrypted. So another one listening to your traffic can't see which certs you're getting. There's still the server name indicator. The host name is still not encrypted. That's work in progress. And that's if you use Python 3 with modern OpenSSL 1.1.1, looks like that. So if the guess is wrong, then the server can tell the client, OK, you guessed wrong. Please try again. And it's still 2 round-trip handshake. But in most cases, it's much faster than even TLS 1.2. And in special cases, you can also do something like a 0 round trip. So if you have already a ticket from the server, you can send a HTTP GET request. In the same time, you do a handshake. And it's like done. So it's the whole request takes like 1 ping back and forth. And that's it. So quick summary. Most importantly, please, please, please use HTTPS everywhere you have. Another thing is there are some plans to improve how we're working with OpenSSL and TLS SSL in Python. We're soon going to move everybody to OpenSSL 1.1.1, even for 3.7 releases. And you get TLS 103 for free, because the old versions are reaching end of lifetime soon. I'm working again on a PAB already started by Corey Benfield. Now we're working with Paul Carra from Python Cryptography. And also have plans to replace certified packages with something more sensible. To close this talk with a quote from a famous Roman, Ceterum censeo certifinem esse delendam. So it means should be destroyed. By the way, I'm considering, or I actually don't know how to translate it into English. Ceterum censeo. Any Latin speakers here? OK, I had Latin in school. And also, there's work on HTTP 3, UDP, Quick. Quick is not actually TLS. It's something even more interesting, which builds on top of parts of TLS. I think Tom is in the audience. Tom is working on fun stuff, so soon to be announced. If you want to learn more, I highly recommend, especially the book on the right side. That's now like 3 years old, but still the best book. Doesn't cover TLS 1.3, but explains the whole public key infrastructure very, very well. For general crypto things, that book is easy to understand and pretty modern. Jean-Philippe Amasson. And several resources. So SSL Labs is really good. If you want to optimize your TLS stack, is tlsfastYet.com. It's from the same guy who makes Heffa Bean Pwned. If you want to dig deeper into the handshake, there's Ulf Heim made a interactive website where you can explore each bit and byte in the handshake and explanation what it does. And this talk is a bit older, like 3 years now, from Filippo. Explains TLS 1.3 and lots of obstacles that took, because they wanted to actually release 1.3 like 4, 5, 6 years ago. I think 2014 was the first try they released that, and they were running lots of issues. And Let's Encrypt is great. And if you don't want to have like public CA, well, the software I'm working on also has a public key infrastructure server. And that's it, right? Oh, on time. Wow. Sorry for rushing that a bit, but again, it's lots of materials, and I already removed like the old horrible parts. But yeah. So if you have any questions, feel free to talk to me. I will be at the conference until Sunday. Thank you.
Thank you.